course, so far, you've probably got the distinct impression that working out areas around irregular shapes is quite a difficult process. But that isn't always the case. In fact, today we're going to look at a super technique which enables you to work out some areas really very nicely. And it's a calculus technique, of course. But we're going to start by looking back at one of the examples that we asked you to do before the program, because the clues lie in that example. So let's do that now.
Well, this is your actual example that Graham was referring to. We asked you to plot the graph of this cubic, x maps to x cubed plus 10, and then we asked you to evaluate and plot the derived function, that's f, x maps to 3x squared. You should have got this parabola. And then we asked you to calculate and plot some areas associated with that function, and here are the sort of points you should have got. Well, I'd like to go back and concentrate especially on the calculation of the areas, because I want to introduce a new concept. It's the idea of an area so far function. So let's go over the calculation of the areas. I want to calculate, starting from the point 0, the area up to any point x under the function f. So starting at 0, the area up to 0 is clearly 0, so that doesn't give me very much. The area from 0 up to 1, well, in this approximation, I can't fit any rectangle here, so again, I'd get 0. But up to 2, I'm going to get this little rectangle, which actually has value 3. And from 0 up to 3, I have to add the value 12, so I'm going to get 15. Up to 4, I add 27, and so on. And that gives me the area so far function to the right. Well, we didn't ask you to do this, but what I'd like to do is to extend this for values to the left of my starting point. So what I'm going to do is calculate the areas to the left. Now, when I do that, I have to use the convention that areas to the left come in with a negative sign. That's the usual sort of convention in mathematics. So the area, for example, from 0 up to 40, up to minus 5 will be minus 90. And so I'm going to get these negative areas here. And then when I plot these values, I extend my curve down here. Now, what is a very interesting exercise is to compare the curve that I finished with the one I started off with. And that's quite easy for me to do, because all I have to do is to actually slip off the curve, slide it down, and see if I can make it fit. Well, in fact, I can't make it fit exactly for a couple of reasons. First of all, I seem to have lost a constant, but we'll explain about that later. Another reason that the fit isn't exact is because, don't forget, I'm using rather crude rectangles to approximate my area. Of course, if I'd have used finer rectangles, I would have got a closer approximation to the area. So we can't expect the fit to be exact. But let's recap what we've actually done so far. What we've done is, we started off with this given cubic curve. We've calculated its derived function f. And then, by means of this area so far function, we've reconstructed this new curve. And the interesting thing to remark is that the shape that we end up with is the same as the shape we started with.
Well, you should have got two things out of that example. The first is that there's such a thing as an area so far function. And the second is that there's a relationship between the function we started with and the function we ended up with. But now I'd like to tell you what this program's all about. It's about working out areas under curves, like this. And we're going to work out areas, say between points A and B, under a curve given from a function f. And the way we write that is the integral from A to B of f of x dx. Now, you have actually seen things like that before. A long time ago in block 2, I think, you saw the function f of x is equal to 1 over x, and you worked out the area between the points 1 and 2, and the answer came out to be 0.6931. Integral from 1 to 2, 1 over x dx is this number, which was incidentally log 2 to the base e. Now, in fact, you could also work out other areas of this kind in simple cases. For example, when f of x is equal to x. That's not too difficult. Here we are. F of x is equal to x. and it's the area here that we want to calculate between A and B. And we get the integral from A to B of x dx is equal to this because, well, it's the larger triangle, take away the smaller triangle, and it turns out to be that. Now, that's not too bad. But as you increase the complexity of the functions that you're dealing with, so the calculation gets that much more difficult. For example, suppose we take the case of f of x is equal to x squared. This time, let's suppose we're trying to work out the area between these 2 points, the integral from 2 to 3 of x squared dx. And it's this, and it looks bad, doesn't it? It's the limit of a sum. These terms here, that's the height of a rectangle, that's the width of a rectangle, add them all up and take the limit as the rectangles get slimmer and slimmer. And by jiggering around, you can show that the answer is that. But it's not easy. In fact, it gets worse. Suppose that you took the function f of x is equal to cos x. Here it is. Say the area from pi over 3 to pi over 2 or something like that. There it is, the integral from pi over 3 to pi over 2 of cos x dx. It's the limit of a sum again, of exactly the same kind, heights of rectangles, widths of rectangles, rectangles getting slimmer and slimmer. But try to work that out, and it's really quite difficult. I think you'd find that quite hard. And in fact, I think I find it quite hard too. But by the end of this program, we're going to show you a really nice way of calculating something like that. But before we do that, we're going to need some other things. And the first thing we're going to need is a good definition of area under a curve.
Remember, the precise definition of the area under a curve, that is of an integral, involves taking the common limit of a sequence involving lower sums and upper sums. In that example that Graham said we had before, we calculated the area under the curve x maps to 1 over x between 1 and 2. And here is the first term of a sequence involving one lower rectangle and one upper rectangle. And as we take more and more rectangles, you see the numbers get closer and closer together. And so we see that the value of the area of the integral is a number which lies between 0.693 and 0.694, as we saw. So in this case, as in every case where the common limit exists, we can take either lower rectangles or upper rectangles to define the area. So in particular, if we want, we can take lower rectangles. If we want the area under this curve, between these 2 points, we can use lower rectangles to give us an estimate. As we take more rectangles, the estimate improves. And we can get as close as we like to the area under the curve by taking thinner and thinner rectangles. That's really using the idea of a limit. We can apply this sort of argument to any reasonable curve and arrive at a value for the area between any 2 points. Now we can use this way of finding the area to make the area so far function more precise. First, we need to fix a starting point. Now, below our curve, we can plot the value of the area from this point to, say, this one. That area has this value. The area from our starting point up to here has this value. The total area up to here has this value, and so on. The area from our starting point up to anywhere in the curve can be plotted below. And that's how we arrive at this area so far function. So using our definition of area, what we've seen is that from this function f and with this starting point, we can construct an area so far function that tells us, for example, that the area under the function from the starting point up to this point here is given by this height of the area so far function. Well, I'd like to extend that a little bit. If I look at my function f, well, at the starting point, of course, the area so far function has to vanish. If I go to the left of the starting point, well, remember my convention that to the left areas are counted negatively, and so my area so far function has to become negative itself. What happens if I go beyond this point? Well, here I'm adding more and more area, so my area so far function has to increase. But at this point, where the function f itself becomes negative, well, we have a new convention essentially that areas below the axis of f are counted negatively, and so at this point my area so far function itself will have to decrease. Well, so far so good. But what we've been promising you is that using this area so far function we could calculate the area under f between any 2 points. So let's see how we can do that. This is the same curve as before with its corresponding area so far function. Suppose we want to find the area from A to B. We know the area up to B has this value, and the area up to A has this value. So the area between A and B is this difference in those two areas, which is just the difference in these two values. So, to calculate the area between A and B, we only need to find the two values of the area so far function and subtract them. So if you give me the area so far function, then I have a very simple method for calculating the area under f between any 2 points. Well, it's certainly a lot easier than adding lots of little rectangles together. But perhaps there's one thing we've overlooked. Surely the area so far function depends on the starting point. Well, let's iron out this problem. This is the area so far function we've obtained from this starting point. Suppose we'd started our area measuring from this point. What would the area so far function have looked like? The difference between this function and the one we had before is just this height. And that's just the area up to our new starting point. If we'd started to the left of our original point, we'd have an extra bit of area to add on. So we don't just have one area so far function, we have many, depending on where we start. And of course, they can take negative as well as positive values. How does this affect our area calculation? For any one of the possible functions, the difference in the function values at b and a is the same. So that means that it doesn't matter which of our area so far functions we take. We'll always get the same value of the area between a and b. All we need to do is to find one of the possible functions.
Well, now we come to a most important part of the program. How are we to find these area so far functions? And you know, the clues are all in that example that we asked you to do before the program. So let's go back to look at that. Here it is. Now look in here. F of x is equal to 3x squared. You work out the area so far to get this curve down here, and let's suppose it is the actual area so far function. And we remarked before that these two graphs look very much alike. But this one at the top differentiates to give this. So isn't it reasonable that this one down here also differentiates to give that? If that's the case, there's a very interesting relationship between area so far functions and differentiation. In fact, there is such a relationship, and it's all bound up in what's called the fundamental theorem of calculus. And that's what we're going to look at next. Suppose we take the area under the curve, f, from the point x to the point x plus 1. We know that this corresponds to the difference in function values of an area so far function at the point x and at the point x plus 1. That's this value. Now we can rearrange that area under f into a rectangle, still with base 1, but with the height h, say. The area under f hasn't changed in magnitude, we've just reorganized it into a rectangle with height h and base 1. So the area is h. So a of x plus 1 minus a of x is also h. Now let's look at the slope of the area so far function a. This chord has slope h over 1, and that's just h, the same value as the area under f from x to x plus 1. Let's take a smaller area with base a half. We can do the same sort of rearrangement as before. Let's call the height of the rectangle we get k. Then its area is a half k. So the difference in function values for the area so far function is a half k. Now look at the slope of this chord. It's a half k over a half, which is just k. So k is the height of the rectangle and the slope of the chord. Let's look at a still smaller area, of width delta this time. This height tells us the magnitude of this area, which we can rearrange into a rectangle with height mu, say. So this height is mu times delta. Now, what's the slope of the chord? It's mu times delta over the base of the triangle, which is delta. So it's just mu. And that was the height of the rectangular area. So height mu on the top picture gives us slope mu on the bottom picture. Well, you can guess what we do now. We ask what happens as delta tends to 0. As delta tends to 0, the heights of the rectangular areas get nearer and nearer to this value, and that's just the value of f at x. The chord approaches the limiting position of the tangent at x, and that's just the derivative at x, of course. So to summarize what we've just seen, as delta tends to 0, the derivative of a at x has the same value as f of x. In other words, a dashed of x is equal to f of x. And of course, that statement is true for any value of x. Well, this result is called the fundamental theorem of calculus. Now I can use that result to solve the problem that I mentioned at the beginning of the program, the integral from pi over 3 to pi over 2 of cos x dx. And I'm not going to use this limit of a sum process. I really don't fancy that a bit. Let's look at a general integral, the integral from a to b of f of x dx. How would you work that out? Easy. a at b minus a at a, provided that we can find capital A. But what do we know about it? Well, we've just seen that differentiate it, a dashed of x is equal to f of x. So in the case we're considering, when f of x is cos x, we get cos x there. So what are we going to put in here? What function, when differentiated, gives us cos? Sine. Sine is the obvious candidate. Sine differentiated gives us cos. But is sine really an area so far function? It's behaving like one. It's got the properties of an area so far function. Differentiate it and it gives the right result. But is it really an area so far function? Well, I can only think of one way of checking that, and that is to look at all the area so far functions that you get from cos. So let's look at that now. Here is the cosine curve, and let's take this point as our starting point. What does the area so far function look like? Now let's take a different starting point, so that the area so far function is 0 at this point. What does the area so far function look like now? Taking lots of different starting points, we'll get lots of area so far functions. But let's do it methodically. Watch what happens to our area so far function as our starting point moves to the right. Now let's move the starting point back to the left, but record the highest curve and the lowest curve. This is the lowest, and this is the highest, and any area so far function must lie between the two. All our area so far functions lie in this band, and sine x is one of them. Oh, well, now it's easy. Integral from a to b of cos x dx is equal to sine of b minus sine of a, because sine is an area so far function. So we've done it for any a and b. But there's one worry, you know. Do we have to go through this process of checking that the function is an area so far function before we can do this calculation? I mean, supposing that I'd chosen in here to guess not sine, but 20 plus sine, because that differentiates all right to give cos. Would it have worked? Well, 20 plus sine isn't an area so far function. It's much too high up. It doesn't fall within this bandwidth that we saw a moment ago. But it still works because, look, you see 20 plus sine there gives us an extra 20 in there and a minus 20 in there. So they cancel out. So the same process works. And any candidate in there is going to be a function which, when differentiated, gives us cos. It's going to be a primitive of cos. And we know that very well that they all differ by a constant. So they're all going to be like this, 20 plus sine, constant plus sine. So now, you see, we've got a very simple process for working out integrals. And here it is. All you do is look for a primitive of the function that you're given. Work out then f of b minus f of a. So you see, the whole business boils down to not finding area so far functions, but ironically finding primitives. You know, the whole program's been about area so far functions, and now we've decided we need primitives. But you know, we couldn't have got to that stage, we couldn't have actually found this technique if we didn't know that the fundamental theorem follows from the fact that we know all about area so far functions. That's the trick that does it.